Hi, good morning and welcome to the ZP Developer Zone webinar. We do this webinar every Thursday at 8 a.m. London time, and we use it as an opportunity to really interact with the sort of members of the ZP Developer Zone. So let me essentially jump straight into it. So we sort of show this slide every week, and we kind of say the ZP Developer Zone, we have a sort of a plethora of resources across ZP. We have the ZP Academy. We have these webinars. The ZP Academy obviously has training courses on this kind of technology that ZP is interested in. There's a couple of free courses on there. I just want to say morning to FTAB. Nice to see you, FTAB. So we have our academy. We have our webinars. We do have our collaborations. With collaborations, I really mean with our sort of academic collaborations. We're slightly unusual that we've actually got two sites in the UK now, a double lab and a 22-person site in the UK, and then and that's actually near the University of Warwick, so that really helps with those kind of collaborations. And we also have a small office on campus at the University of Swansea. So with time, these we'll have more and more of these, and it really helps with collaboration. It won't all be in the UK. This will be across the globe that we'll be essentially doing this. And then we also have the jobs that we make available through the ZP Developer Zone, and we also have our website for the ZP Developer Zone members, and we also have our how do I put this? We also have the website as well with all the essentially data for the members. Now tomorrow, I just want to say we're having a workshop. It's rather early. There's a free workshop being run from India. ZP is coming online to do this workshop at around about 6:30 a.m. London time. That'll be obviously about 7:30 a.m. In Europe, and that'll be about 1 p.m. In Indian time. So we are going to do a live streaming workshop tomorrow for those who are interested. And if you're in India, the best way to find out about these kind of things is contact Technando. Now, we try to use these webinars to essentially help answer questions that come in from various people, including mostly our ZP developers or members. So this week we've got a question about potentiostats. We have a question about microfluidics. We have a question about screen printed electrodes, and we have a question about modifying screen printed electrodes. So I'll talk about a potentiostat from a company called Zana, the Zennium X. I'm also going to do a demonstration on Djuli as well, because Djuli has really been expanding recently. With Djuli, you can transfer data to Djuli using things like apps on the smartphone, or Djuli is also a database that allows you to upload electrochemical data and you essentially upload it, share it, analyze it. You can do it essentially all in the cloud. So we will also talk about Djuli. I'm going to talk about a bit quicker because I realize I haven't got all the time in the world today. We're also going to talk about microfluidics. Anyone who's developing I wouldn't say diagnostic, but a detection system using screen printed electrodes. One of the important pieces that people don't always take into account or don't always do is actually how to retain the sample on the sensor or near the electrodes. And at ZP we do have a good technology around doing that. We have some questions come in just about our biosensors and our screen printed electrodes, and I'll touch upon that. And then there's also a question about modifying screen printed electrodes. So I'll use the hypervalue electrode or the carbon electrode from ZP to talk about that. So like I said, I'm going to do a demo, and I'm going to show you how to upload data from the Anna Pot or from the PalmSense. I'm also going to show you how to upload data from CH Instruments, and I'm also going to show you how to upload data from Autolab. But as I say, that will be in a bit. First of all, we had an inquiry where somebody is really looking to do like impedance spectroscopy, and they were asking about the Zennium X. If you're not familiar with the Zennium X, this is something that ZP does distribute. The Zennium X is kind of one of those larger type of impedance spectrometers. I mean, this is sort of an image of it here. I thought the hand in the image kind of gives you a sense of the scale. It's definitely something that it gets delivered by a courier, and yeah, you have to pick this guy up and put it on the bench, and it's not going to move. And that is actually a bonus sometimes. That some lab instruments, we've got a lot of those at ZP, they're getting quite small, so they sort of fly around the bench and stuff. Well, to be fair to the Zennium X, it's not flying around the bench. So its size is both, it takes up bench space, but at the same time, it does give you a good anchoring point when you're doing the experiments. Now, it does have very good accuracy. It does have these kind of 32-bit converters in it. So the Zennium X, I kind of consider it a real, somebody who's really interested in EIS and really making sure that the EIS is really kind of accurate, high resolution. The Zennium X is that kind of instrument. It has an excellent frequency range. It's just me, but I always laugh when people, when you say 10 microhertz. I mean, what's the difference between 10 microhertz and DC? But it does have that capability of doing very low frequency, and then 12 megahertz is fairly high frequency in electrochemistry. I think one of the big bonuses on the Zennium X potentiostat is the ability to actually do fast electrochemical experiments, so fast CV. Now, other potentiostats use an awful lot of maths, a lot of smoothing in order to kind of give you decent looking data. And when there's a lot of mathematical manipulation of the data before you see it, then you're really hiding the true results. That you don't see the raw signal. Actually, what you see is the raw signal that's been smoothed, and then you see that, and then you interpret that, and you think, oh, that's therefore my constants are this. Well, actually, you don't realize that you've actually gone through quite a few smoothing algorithms before you see the data. So I think one of the benefits of the Zennium X is the ability to do really fast voltage changes, and for it to, what you're seeing is let's say the unsmoothed, it's the raw data rather than something that's gone through somebody's smoothing algorithms that you don't know about, but actually it can end up changing the time constants that you're looking at, and you could end up publishing it. One of the bonuses, let's say, of the Zennium X is really this compliance voltage. This compliance voltage is the sort of voltage that, if I say I'm going to apply 5 volts to the working electrodes in a 3 electrode setup, you need to go and apply a you have to apply a voltage to the counter electrode to make sure that the current at the counter electrode can keep up with the current on the working electrode. Now, on smaller potentiostats, you don't realize this, that you might be applying 1 volt, let's say, to the working electrode, but there's such a resistance at the counter electrode that the compliance voltage is not large enough from the instrument, and so actually you're getting a kind of limited current at the working electrode because you didn't realize that the compliance voltage wasn't large enough at the counter electrode. So this is something that some of us don't understand, but the Zennium X does have this large compliance voltage, which means most of the time, if you're applying up to 5 volts on the working electrode, there's more than enough, let's say, power in the instrument to be able to apply a compliance voltage to the counter electrode, and it can carry on doing its job. I would say that the Zennium X is really built for kind of power applications, that you can add these, you can apply plus or minus 5 volts or plus or minus 15 volts. It's as they say on the website, it's really designed for sort of, things like battery applications, fuel cell applications, maybe photovoltaics, but the kind of power type fuel cells, those kind of power type applications. They do have good AC amplitude. They do have a modular approach. It's almost this framework that the Zennium X is in. It's almost got a series of cards, and you can pull the cards in and out, so you can really sort of change the configuration of it. And there's a lot of flexibility in the Zennium X. You can kind of change, if I got a floating ground or if I got let's say a grounded ground. So those kind of things are definitely at your fingertips in the Zennium X. It also, I checked its lower range. Now, at Zimmer and Peacock, we are particularly interested in sort of electroanalytical chemistry, and then as a subdivision of that, biosensors. And so, the kind of currents that we're interested in, are are often much smaller. You know, we're down in the sort of nanoamps and microamp region. So I see that the Zennium X also does that as well. So I said it had power application, but it also has, you know, nanoamp application. Now, when people ask me to recommend a potentiostat, I do, you know, tend to have a look at the papers that they're working upon. So in this particular case, you know, I was kind of having a look at relative or papers that were associated with the group, and it kind of gave me a sense that a lot of the work they do is, you know, when I say milli electrode, I'm kind of thinking of kind of glassy carbon electrodes, you know, sort of 4mm diameters. So that tells us something about the kind of current ranges. So this group is in sort of material science, the characterization of materials, the synthesis of materials, their applications of materials, but these do feel like fairly large electrodes and fairly high currents, and that does really put them into the sort of Zennium X type category. And I did look at a couple more papers, and I did see, you know, the sort of modification of glassy carbon electrodes with nanoparticles and then using them for oxygen reduction. That definitely feels like a sort of 4mm diameter glassy carbon electrode, a kind of traditional, you know, electrochemical setup. Now I'm going to go a bit faster because I realize it's 8:10 here, so let me sort of go a bit faster. But I would say, you know, from those papers and from the descriptions, you know, yes, you know, they are doing fairly large electrodes, and they'll have fairly high currents, and the Zennium X, you know, should fit into that quite nicely. Just want to do a comparison between, you know, the Zennium X and then two other potentiostats that we apply at that we supply at Zimmer Peacock. We apply our own Anapot EIS and also the Palm Sense 4, which also has EIS. I think it's nice to just compare these two, because everyone wants one instrument that does everything, but, you know, in fact, you know, some instruments are better at, you know, high voltage, high current, and some instruments are lower cost and, you know, are okay for low current and lower voltage applications. So if we compare them, I'm pretty sure that Zana, who make the Zennium X, they've actually got the oldest, well, they've been on the market the longest. So for commercially available electrochemical impedance spectrometers, I really think that Zana is actually the longest running company in this space. I mean, I think, you know, from their website, they started in 1976. I absolutely know that there's only a few of us on this webinar today who were born before 1976. So these guys have been doing it a long time. It's also worth saying that, you know, instruments like the Palm Sense, you know, they have a long history as well. You know, that the original founder of Palm Sense, you know, was actually sort of, I think, also a founder at Autolab. So they do have, you know, long histories. But I think Zana and the Zennium X, you know, wins on length of time in market, length of time in development. The Zennium X is large, which I said, you know, is, you know, you could see it as a downsize, but actually the size, especially in power applications, you know, makes it quite a stable platform. I was told by one engineer once, you know, that he opened the Zennium X up, and he just said there's a massive copper sort of bar in the back of it, you know, and that sort of, you know, speaks to the amount of engineering that there's in there. So I can understand why they're sort of so stable, because Mo Aftab's just saying, yeah, he's a 90s kid. Yeah, I know what you mean. So the Zennium X is large, but actually that largeness does actually lead to a very stable you know, instrument. And, you know, the Palm Sense or the Anapot EIS are small, you know. So hi, good morning, Ahmed, nice to see you this morning. Now the Zennium X has a lot of features in its software. Its software is complex, and so I would say that with the Zennium X, you need to really be a dedicated user. You know, it's not the kind of instrument that I would necessarily say you just walk up to. It'll just basically just do about everything you can imagine, but you know, it's got decades of work in that software, and you really have to be kind of, you know, a dedicated user to really sort of use that software. Now I would say that the Palm Sense or the Anapot EIS, I mean, the software is simple. I've barely ever read our own manual, you know, and I can use it, and I really think actually it's, you know, you can be a technician or a junior scientist and you know, the software behind the Palm Sensor and a pot EIS. You can just walk up to it. So it really, when you're thinking about the Zennium X, you kind of think, you know, is this going to be used by a dedicated user or going to be used by lots of junior scientists? You know, it is part of the kind of consideration. The Zennium X gives a very pure signal. There's very little mathematical manipulation of the signals that you're seeing. Whereas I was just in a conversation with a guy I admire, you know, and he is saying, you know, some of the smaller potentiostats, you know, there's a lot of filtering, a lot of averaging going on before you see that signal, which is more important when you're trying to do fast transient type work. You don't want that. It's going to give you longer timelines than are really associated with the signal. The Zennium X, I would say, is optimized for sort of power applications, where I think some of the smaller potentiostats, they're good enough to be used in low current, low voltage applications. So I just want to give you kind of some of my opinions on or the differences between these types of instruments. The Zennium X is large and heavy. That can be, you know, a negative if you want to move around a lot, but it's also a positive that it will sit on the bench and it won't go flying off. And you know, you'll see from some of our demos sometimes when we're demoing the Anapot EIS, we do knock them with our hands sometimes and they move, you know, and it can be a bit annoying, you know, in the middle of an experiment. Now, I think I'm going to do a demo now of the Djuli software. So Djuli, I felt because we're talking about a lot of potentiostats this morning, I wanted to just give an update on Djuli. So Djuli is very, at the moment we've got it configured so that we can receive data from the Anapot, the Palm Sense, the CH instruments, or the Autolab. And I've actually put together by the way, any links you see popping up this morning, I'll definitely have those links. Underneath the video or underneath the YouTube video afterwards. So yeah, there'll be a link and I've got some software there for you to basically practice. So I'm just going to do a quick demo. So let me just go to my computer. And what I'm going to do is Djuli obviously is a cloud database. I think it's very powerful these days. You know, you can essentially upload data, analyze data, and store data. And now we've started to make it compatible with other people's, let's say, files from their potentiostats. So as I say, there's a page where you can actually download Palm Sense data, CH instruments data, Autolab data. I'll put the link underneath the video. I'm into the Djuli at the moment, and you can just, for example, click on here. I can see the CH instruments data. I've added it to the database. I can go to properties. I can say this is a discrete experiment, voltage microamps, and it's basically just imported the data. You know, so that shows you that we can actually upload the CH instruments data, no problems. What I'll do is I will just also show you that we can, oh, by the way, with CH instruments, they have a native file format. What we've done is we exported it essentially as a text file. So just FYI, if you're using CH instruments, export it as a text file. This is a Palm Sense file. We left this one as the sort of native format. We didn't do an export. We just saved the data, and then we can essentially upload the data, which is what I'm doing here. And that uploads that data, so that's pretty useful. There's an awful lot of Autolabs out there, you know, so credit to Autolab, but we can also upload their data as well. Now their data here is it's exported as essentially as an Excel file, but we've obviously, you know, tested that we can actually upload all of this essentially data, and we can upload it. And now I haven't shown you the analysis parts, but it's worth saying that there's an awful lot of, you know, delta fit, single peak, averaging, baseline subtractions. We've got a lot of let's say data processing capability in Djuli, and I like Djuli because essentially it's kind of operator independent. You know, it's not Mac based, it's not PC based, it's not Chrome based. You know, it's up in the clouds. You know, so it really gives us kind of scalability across applications. So It's free to open an account on Djuli. As I say, I've got a landing page for you. You can download the software and you can just have a little play with it yourself. So I will jump back now to our sort of main topics. But I just thought that Djuli was relevant, seeing as we're considering talking about a range of potential stats this morning. Now, Djuli also, I am going to speak very fast now. At Zimmer Peacock, we're an ISO 13485 contract developer and manufacturer of screen printed electrodes. So Djuli really plays a role also in our development and manufacturing programs for people. So we we have these screen printed electrodes that are available into the client projects. They get functionally changed. It's really important. We're going to do a talk in a minute on microfluidics. So we're also very good at adapting them so they have things like capillary fill on them, so the sample can get sucked in. It really helps with the user experience. It's funny that we've actually been talking about large and small potential stats this morning. So we have this is a hand-sized instrument that is essentially a potential stat that can just do just about anything. Square wave voltammetry, differential pulse voltammetry, EIS. It can do a lot. But what makes it do what it wants to do is because, in fact, we have Android apps and we can also do iOS apps. It's the app that tells the meter what to do. And so that means that because it's app-based, if there's some reason that we need to update essentially the firmware, we don't update the firmware on the instrument, we actually update the app. So we tell the app what to do, the app tells the meter what to do, the meter does essentially the experiment, the data comes back to the app. And then this is why I earlier on showed you that Djuli is a cloud database where you can upload data, you can analyze data, and you can actually share data. But Djuli is also basically a scientific engine with a sort of strong bias towards electrochemistry, because these apps that we build can actually send the data to Djuli. Now, whether you show Djuli to an end user is like a commercial decision, but essentially you can send the data to Djuli where you can do all the processing of the data, at which point then you can give the data back to a client through using something like an API, an application program interface. And you could also just do it by having a sort of login, and you can give somebody a very kind of clean login, give them a result. Was this a genuine sample or was actually a fraudulent sample? Was this a diagnostic result that was positive or a diagnostic result that was negative? You can give them a very clean, you don't have to give them the scientific interface. But the nice thing about Djuli, especially in development, is because of the data analytics on it, it allows us to extract features from the electrochemical data, and then we can also, especially when you're doing development, and you know whether a sample is a positive or negative, or how much analyte is in material, you essentially know the truth. And if you know the truth, then you can use AI to align the features from the electrochemical raw data with the truth, whether it's positive, negative, authentic, or a particular concentration, and then come up with a really robust algorithm. So the reason I say all that is because I want you to go up, get a Djuli account, upload the data, play around with it, but also know that there's it's really, though we're using it as essentially a sort of electronic lab notebook where you can upload data, analyze data, share data, it's also a scientific engine that we can actually use in more, let's say, consumer-facing applications as well. But I will go on, speak a bit fast. It's 8:24, I realize we're running out of time. One of the questions that came in, this is only question number 2, was, do we functionalize screen printed electrodes before the microfluidic channel or after the microfluidic channel? The quick answer is, we functionalize electrodes before the microfluidic channel. You don't want to do it within the channel. You can if you want, but I don't think it scales particularly well. So the quick answer is, and if you want to make these kind of capillary or microfluidic channels on your screen printed electrodes, we do have kits on our website that allow you to essentially make pieces like this, and it all works pretty well with our hypervalue carbon electrodes, and I put a little link to that there below as well. It's also worth saying that we've been making a lot of 3D printed pieces for our hypervalue electrodes, so people who are interested in doing fluidics, microfluidics, we have put quite a lot of 3D printable files available. So anyone who's a user of our hypervalue electrodes, especially the carbon ones, We do have some STL files that we can give you, and you can download and make 3D printed features for those. And we do have some, some other links also to the ZP Developer Zone where we store some of these files. So anything that you see as a link on my, let's say, presentation, I will put it underneath the video. Also, if you are playing with ZP sensors, to get the, especially in the R&D phase, if you are getting them, please get hold of some of these 7mm connectors as well, because it just means that we're connecting properly. There's nothing worse than having rubbish data because you're not making a good electrical connection to the electrodes. Question 3, and I'm sorry, I am going to speak a bit faster now. And we had some inquiries really asking questions about the PDF catalog. I actually took the PDF catalog down because I realized that PDF catalog's been sort of 5 years out of date, and I think it's causing more confusions than anything. But the questioner was asking about potassium and pH, and I will answer that. They were asking a lot about our gold electrodes and our platinum electrodes, and they were also asking about what the suffix ISTCL. This suffix basically means that we have a version of our sensors or screen printed electrodes that we call them chloride resilient. For some applications, you can't always be dependent on the chloride concentration in the sample to be constant, which means that your referencing electrode or your reference electrode could have a variable voltage, and in those situations, we need to fix the chloride concentration on the reference electrode. So we do have some technology to do that. In many applications, I don't suggest it because people expect that reference to be really stable. It's stable to a degree, but it's not, it's not stable for months and months. If you're running like a 5 millimolar chloride concentration over one of these electrodes, the electrode will end up leaching the chloride into that solution. So I think it's good to work on applications where the chloride is fixed. One way of fixing the chloride in your application is what we do, which is actually to have the salt deposited on the electrode. So when the sample comes in, it picks up quite a lot of salt and therefore fixes the chloride. You can do it the way we're doing it here by having the chloride actually immobilized on the reference electrode using a polymer. Also, in many samples, the way we do our chili sensing, we take 1 part of chili and add it to 4 parts of buffer, and that helps to fix the chloride as well. So I don't necessarily recommend those electrodes from the very start. They're a bit nuanced in their use. We do have an awful lot of biosensors, and it's probably worth saying that any questions you have about the biosensors, we generally do have information on the website about them. So we do have, now the electrodes I actually recommend are really we've got the value screen printed electrodes. We've got gold, platinum, and carbon. These are the guys that we're making a high volume. We offer them in fairly low cost. And then really it's the hyper value carbon electrode that I'm sort of recommending most people these days as well. Recommendation on the pH electrodes. We have a lot of pH electrodes. Just a quick recommendation. I quite like these pH electrodes that are based on our hyper value electrode. I like them because they're fairly low cost, even at low volume. And we generally ship those in 3 to 4 weeks. Really no issue. Recommendation on the potassium is to use our simplest potassium sensor. The price is not as attractive as the pH because it's based on ceramic, not polymer. And that again ships in about 3 to 4 weeks. Question number 4: How do I work on the working electrode without touching the reference electrodes? So we do this an awful lot. We would take one of our electrodes. At small scale, we might do hand pipetting. At large scale, we'll use a robot. But we'll take that carbon electrode. We'll put 3 sort of drops, of functional material. This functional material could be aptamers. It could be essentially RNA for doing RNA binding. It could be antibodies. We've got all sorts of materials. But we sort of put 3 drops like that. Those 3 drops coalesce. We let it dry. We're very careful about the drying. If you don't add in a repeatable manner, you certainly won't get a repeatable sensor. And if you don't dry in a repeatable manner, you certainly won't get a repeatable sensor. But we then dry it. The other way of functionalizing that working electrode is to do electrode deposition. So we will do, a drop of solution that covers essentially all 3 electrodes, and then do something like electropolymerization or maybe electroplating. But electrochemical techniques can also be used to functionalize those working electrodes as well. So it's 8:30. We do this for 30 minutes. I'm respectful of people's time. So question 1, potential stats. Question 2 was about microfluidics. Question 3 was about, what electrodes do we recommend? And question 4 was about modifying the SPE. So the Zennium X is an excellent potential stat. It's probably the oldest, and I mean that in a good way, oldest potential stat on the market. It's super stable. There's a lot of features in the software that it's almost take you 3 years doing your PhD to kind of learn all of those features. It's probably worth just saying that, I think one of the big problems in electrochemistry in the lab is the data is very isolated. It's on people's C drive. So, if you're starting a series of electrochemical experiments, get yourself a Djuli account. If you have problems with it, you find us quite supportive and we'll get it up there. If you're doing microfluidics on screen printed electrodes, do the functionalization before you make the channels. It's hard to go into the channel afterwards and functionalize the electrodes. We do have a lot of information on our websites about and I've recommended a potassium sensor and a pH sensor, and I've recommended some screen printed electrodes. And then modifying the SPE, you can do drop casting on the working electrode. We use a robot a lot. I think one of the questions was, should I actually modify the ink, or should I modify the electrode after I printed it? I would say when you're in your development phases, I would be modifying the electrode post-printing. And if it's all working and you're going to super large scale, then you can start investing time in modifying the ink itself. But you're kind of, you want to make sure that everything's working. And I would actually say print the ink, then modify it. Later on, I would maybe go into modifying the ink itself. But if you start off with the idea that you're going to modify the ink, and if your assay for some reason doesn't work or is not commercially viable, you kind of waste a lot of time doing that. I would actually say print the ink first, then modify it, would be my advice. So thank you very much. I appreciate that was very long. Don't forget there's a webinar tomorrow. It's 6:30 London time. It's 7:30 European time. It's about 1 o'clock. It is, I think, 12 o'clock rather, Indian time, and it's free to sign up. There's a lot. We're just doing it as part of a long e-conference. Okay, guys. Well, thanks very much. I appreciate your attention this morning. Nice to see you, Aftab and Ahmed. Appreciate the support, and speak to you soon. Okay.